Hi everyone. In the last video we learned about the ability of water vapor to store enormous amounts of energy, and in fact kilogram for kilogram water vapor has the potential energy of several atomic bombs. You can start to see that in the power of the atmosphere that you're seeing right here. So let's explore how to release that energy and what causes violent storms. So in releasing that energy, we are cooling the invisible water vapor in the atmosphere to condense that water vapor and produce that huge cloud that you saw. In order to cool that water vapor, we are reducing the temperature of the water vapor in the atmosphere. When we are reducing the temperature of the water vapor has falling kinetic energy. That energy is being reduced. The energy has to go somewhere. It's transferred to the air, to the environment, and the air or the environment has rising kinetic energy, so the temperature is going up in the air. That means that cooling water vapor warms the environment. And when we get to the point where we can condense the water vapor, we've reduced the temperature down to the point where the gas can condense, it will stay at one temperature as it's a combination of water and vapor. As it's in the process of condensing, it releases the stored latent energy from the vapor into the atmosphere or into the air. That means that the water vapor is going to have less energy than it had before. With less energy, you are promoting more stable and less energetic bond formation in water. And you are increasing the amount of energy in the air as well. How much energy is that? Well, that energy is called the heat of vaporization. And when you are condensing vapor, you are releasing that latent energy that you collected on the way up from the boiling water to the vapor. That heat of vaporization is 539 calories per gram of water. Now, that's an amazing amount of calories per gram of water. And so you begin to understand how producing a cloud releases an enormous amount of energy into the atmosphere. Let's look at what happens with water to ice. And what happens there is that cooling water will have falling kinetic energy and will send that energy into the environment. In this case, the environment could be the air, but let's think about this water being on pavement that could ice up. So the environment could be the air, but let's think about the environment as being the pavement. As the water loses its kinetic energy, the pavement is gaining kinetic energy. And that means that cooling water warms the environment. When it comes to the fact that you've got water cooled all the way down to the freezing point, that means that this water at 32 degrees Fahrenheit or 0 degrees Celsius will start to become a slushy ice and water mix. It will release the stored latent energy that the water had. In releasing that stored energy, this slushy mix is going to have less and less energy, which means that the more stable ice bonds with less energetic bonds will start to form. And as this latent energy continues to be released, it will continue to energize the environment. It will continue to energize the pavement. How much energy will that mean? In this case, the phase change of that slushy mixture is called the heat of fusion. And that seems like it should be the heat of slush, right? But it's called the heat of fusion because it is associated with the move from ice to water and from water to ice. We actually use a negative value when we are releasing heat out to the environment. But we call it fusion because it's like jazz fusion. It's really smooth heat that is associated with flow, like jazz fusion is, and flow is associated with water. That heat of fusion is 80 calories per gram. So for every gram of water, it's going to release 80 calories of heat. And that's not nearly as great a heat release as vaporization, especially when you consider that the vaporization is per gram of vapor. And that's just an enormous amount of energy because a gram of vapor is an enormous amount of vapor. The heat of fusion is less dramatic, but it's very important for things like the formation of dry ice on pavement. And what we know about freezing warms the pavement. To reiterate, water vapor is invisible. Invisible. This is not water vapor. This is actually hot liquid water that has condensed. So now you're beginning to understand more about these phase changes. But invisible water vapor has tremendous stored energy. And in addition, we can look at that water vapor in a real life situation in the environment and understand a little bit more about how that water vapor and its condensation can warm the environment. So the elk here, I think it's an elk. People tell me it's a moose, but I'm pretty sure it's an elk. The elk here exhales and moves out its warmer and its breath full of water vapor. It's right here right now. It's the gas moving out of the elk's mouth. As it moves farther away into the cold air, the gas will release its energy into the cold air. In doing so, it will start to condense and you will see the cloud. So this is an example where releasing the energy from the warm breath will warm the environment, and this will condense into a cloud as well as it cools. Here's another example that you can't see it often. You can move straight from water vapor and not even move into condensation, but move straight from water vapor to ice. That dramatic move that completely avoids water is called deposition. An example of that is frost on your windshield. This is not ice. This is crystallized, this is not ice in the way we think of smooth ice that had been water and froze to ice. No, this is water vapor that crystallized as ice on a windshield. It went straight from water vapor to ice. That's called deposition. It releases all of the water vapor energy and all of the water energy as it becomes ice. This this graphic from your book is very, very important. You're going to need it for tests and for quizzes. Well, you're going to need it for quizzes. And what it says is, as you move from the state of matter of ice through water to vapor, you're taking energy out of the environment in order to break the bonds of the ice to become water, in order to break the bonds of the water to become vapor. You're taking energy out of the environment, and the environment is getting cooler as a result. When you go in reverse and release the energy, you're moving from water vapor to water, and you're releasing the extra energy out into the environment to warm the environment. When you're going from water to ice, you're releasing extra energy. Sometimes it goes to the pavement. Really important graphic here. Please stop the video and study that. All in all, the latent energy transport process acts to bring in sunlight, energize the water to water vapor with an enormous amount of energy. That water vapor rises and cools and starts to release its thermal energy until it meets the point where it can form condensation, and then it releases its latent energy. So two forms of energy there. The rising air rises and slowly starts to lose its thermal energy, comes down to the condensation temperature, then condenses and releases its latent energy. That's an enormous amount of energy. See you on the next video.